Good morning. Today we're going to talk about section 5.7 entitled The Difference of Two Squares. Well, let's refresh our memory, and I want to look back into one of our earlier sections on factoring and recalling the special products. Well, we had three different special products. One was the square of a binomial sum, and if we ground that out, either with the FOIL method or by recognizing our special pattern, it's going to be x squared plus 6x plus 9. Basically the square of x here, x squared, the square of the last term there, 9 here, 3 squared is 9, and twice the product of x and 3, namely 6x. So anytime I see a plus b squared, I can always multiply it instantly if I recognize the pattern. A squared plus 2ab plus b squared. Similarly, we saw that a minus b squared turned into a squared minus 2ab plus b squared, similar to the binomial sum squared, except the middle term would be negative here. The outer and inner products would both be like terms and negative. All right, what I really want to get to here is a plus b times a minus b. Remember, those were conjugate. We call those conjugate binomials, where only the sign in between differed. Right? They're not negatives, they're not opposites, but the sign in between is different. And we saw that when we multiplied conjugate binomials, got a difference of squares pattern. Well, if we're going in this direction, we're multiplying. What I want to do is be able, if we are able to recognize this pattern, we can go the other way and factor it. So I want to factor difference of squares patterns according to this formula. Let me show you what I'm getting at. If I ask us to factor, for example, x squared minus 81, well, I know that's going to break down as x plus 9 times x minus 9. Check it out. If I multiply to check, x squared is my first product, minus 9x plus 9x, the inner and outer products cancel out, and the last product is, of course, a negative 81. So if I can spot a difference of squares pattern, I can instantly break it down into a product of its prime factors according to this pattern. Factor again. Say 49x squared minus 16. Well, 49 is a perfect square. X squared, of course, is a square, and 16 is a square. So I think we can see this as a difference of squares pattern. So it's going to break up as a product of two conjugate binomials. The first terms, of course, are going to be 7x in the first slots. The last terms are going to be 4s with a plus and a minus in between those two binomials respectively. You can check your answer easily. First product, 49x squared. Outer and inner products, plus and minus 28x, so they cancel out. And the last product is minus 16. So this is my final answer here, 7x plus 4 times 7x minus 4. All right, that's an implied product there. And of course, multiplication is commutative. Of course, you could rearrange any factors of a product as you so see fit. So either of these answers are okay. They're both acceptable. Okay? Again, factor 81p squared minus 25. Alright? 81 is a perfect square. P squared is a perfect square. 25 is a perfect square. So I claim I can break this into prime factors according to our difference of squares factored pattern. First term is going to be 9p. Last term is going to be 5. The square root of 25 is 5. And one's positive in between and one's negative in between. Final answer, 9p plus 5 times 9p minus 5. A breeze if you recognize the pattern. Factor 64a to the fourth minus 25b squared. Well, 64 is the square of 8. 25b squared, that's the square of 5b. And a to the fourth, well, I think we can see that a to the fourth is the square of a squared, is it not? So I think I can break this down as a difference of squares pattern. The first terms will be not 8a, but 8a squared. Check it out. 8a squared times 8a squared is 64a to the fourth, is it not? The last terms here, well, 25b squared. What's the square root of 25b squared? Of course, it's 5b. And according to our pattern, one of these binomials is going to be a binomial sum, and the other one is going to be a binomial difference. Hence, the final answer, 8a squared plus 5b times, it's an 8 there, 8a squared minus 5b. Alright, factor. Let's try to factor x squared plus 1. Well, kind of a trick question here. This is not a difference of squares. This is a sum of squares. And a sum of squares is always prime. And if I try to break this down, well, I can only use x's in my first slots. 1, there's only one way to break up 1, and that's 1 times 1. And if you have a plus and a minus, that's not going to work. You're going to have a last product of minus 1. If they're both positive, that's not going to work. You're going to have an inner and outer product that don't cancel out. And similarly, if you try a negative sign here, well, that's really equivalent, is it not? The inner and outer products will cancel out, but your last product will be a negative 1, not what you need. None of these options work, so please keep in mind that sums of squares will always be prime. Factor x to the fourth minus 1. Well, 1 to any power is 1, so I can easily see this as a difference of squares, can I not? I'll have x squareds in the first slots, 1s in the last slots, and a plus and a minus sign respectively between those two binomial expressions. Alright, now notice, this sum of squares factor is prime, as we stated before. Sums of squares are always prime. This can be factored again. Alright, so we're going to factor twice in the same problem here. Don't forget to carry your prime factors down to your final answer. Of course, x squared plus 1 turns into x plus 1 times x minus 1. So this is my completely factored final answer. X squared plus 1 times x plus 1 times x minus 1. Factor a to the fourth power minus 81. Alright, well, a to the fourth, I can view that as a square. 81 certainly is a perfect square, and I've got a negative sign here, so I can view this as a difference of squares and break it up according to our pattern. First terms are going to be the square root of a to the fourth, which is a squared and a squared. Last terms are going to be the square root of 81, 9 and 9. And again, opposite signs in between. A squared plus 9 times a squared minus 9. A squared plus 9 is a prime factor. It's a sum of squares, always prime. But a squared minus 9, just like in the last problem, I can factor it again, break it down again. So don't forget to carry your prime factors down to your final answer. A squared plus 9 factors, of course, is a plus 3 times a minus 3. Final answer right here. Okay. Let's do some harder ones here. Factor 2x to the fourth y minus 32y. Well, 2 is not a perfect square. 32 is not a perfect square. What can I do here? Well, as we said in previous sections, always look for a GCF first in any factoring situation. Alright, the GCF here is going to be 2y, is it not? I can factor out a 2y, and the remaining binomial factor then will be x to the fourth minus 16. Alright, so we factored once with the GCF factoring. Now I'm going to factor again with a difference of squares factoring. So I'll have 2y times x squared plus 4 times x squared minus 4. Alright, so I've factored twice in this problem so far. This is prime. Again, sum of squares is always prime, but again I can factor a third time here. X squared minus 4 breaks down again, does it not? So I'll have 2y times x squared plus 4 times x plus 2 times x minus 2, factoring that final difference of squares factor here. There's my final answer. 2y times x squared plus 4 times x plus 2 times x minus 2. New screen, please. Alright, try something like this. Factor. Now factor means factor completely. Factor it to your... all the remaining factors in your answer are prime. Can't be factored any further. Alright, clearly I see a 3 as a GCF. Alright, so I have 3 times a to the 4th minus 1. This, of course, is a difference of squares. So I can factor a to the 4th down, factor a to the 4th minus 1 down to a squared plus 1 times a squared minus 1. Again, a squared plus 1 is prime. It's a sum of squares. So I'll carry it down to my final answer, but this factors again. I'll factor a third time. A squared minus 1 factors as a plus 1 times a minus 1. Final answer there. Let's see, 3 more I've got here. Factor. Alright, this one may seem a little screwy. Now let's take a look at this. This is from our homework list, a little bit harder one. 64b minus 4b to the 5th power. Well, b to the 5th power, I can't see that as a square. So, well, what am I going to do? Well, of course, I'm going to look for a GCF first. GCF first. And then I think things will fall into place. What's the GCF of these two terms? I believe it's 4b. So I can factor out a 4b, and I'm left with 16 minus b to the 4th power. Alright, now I've got, in this difference, I've got a constant first and a variable expression second. Still, it is a difference of squares, is it not? So I can break down this further. Carrying 4b down, I'll have a 4b plus b squared times 4b minus b squared. Oops, sorry. Made a mistake here. Hang on. It's 4 minus b squared. Minus b squared times 4 plus b squared. In other words, this expression here, I'm underlining in pink, breaks down into this product down here. Back to yellow. Alright. 4b minus b squared, 4 minus b squared, that is a difference of squares. I can factor that as 2 plus b times 2 minus b. And again, don't forget to carry down your prime factors to your final answer. Again, this expression here is prime. Sum of squares is always prime. Alright, so here's your final answer. 4b times 2 plus b times 2 minus b times 4 plus b squared. Alright, 2 more I want to talk about today. And I got this one from your homework list, little nasty one here. 144a squared t squared minus 169b to the 6th. Alright, don't panic. 144 is a perfect square. It's 12 squared. A squared, t squared is the square of at. 169 is a perfect square. It's 13 squared. And b to the sixth, I can really view b to the sixth as b cubed squared, could I not? Alright, so I can look at this binomial difference as a difference of two squares. I'll need 12at in the first slots. Check it out. 12at times 12at is this first term, 144a squared t squared. What's the last term's going to be? Well, 169b to the sixth, I claim it's 13b cubed in both last slots. Check it out. The last product is 169b to the sixth, is it not? And according to our pattern, all I need is different signs in between in these two binomial expressions. So I'll say one is positive and one is negative. So there's my final answer. There was no GCF here, but still I could factor it pretty easily if I recognized the pattern. Alright, last one. Factor. Uh-oh, this one's got a fraction in it. Well, fractions can still be factored. Notice, 136 is really the square of 1/6, is it not? 1/6 squared is 136. And if I can view this as a square, and of course y squared is a square, I can break it down according to my difference of squares pattern. One's going to be positive, one's going to be negative in between. 136. Well, I claim 1/6 times 1/6 is 136. So 1/6 is going to be my first terms. Y squared, only one way to break down y squared really, y times y. So I've got 1/6 plus y times 1/6 minus y. Final answer. Alright, I pretty much covered every type that's in the homework assignment. We'll call it a day with section 5.7, difference of two squares.